Okay.
So the thing I guess that's maybe different out of this, I'm trying to think about this, how to best describe it is we know that the counts for white-tailed deer are 3,500, 1,000, and 500, but these are not the expected counts. These are just the, I'm sorry, these are the expected counts if you had this many. So we really need to convert all of this to percentages or proportions. So I'm trying to say here. So like think of white-tailed deer. It's really 3,500 over 5,000 or 0.7.
Okay.
The 1,000 is 1,000 over 500, which is 0.2, or 5,000. The 5,000 is 500 is 0.1. So what I'm trying to say is you cannot work directly with these counts, even though we almost always work directly with the counts. Even like all the problems we've been doing, we've been working with counts.
Right, right.
So the observed, we've got to do somewhat of the same thing here. The observed is 138 out of 166.
Okay.
And that's whatever that is. Okay, we'll get that number in a moment. Then it's 23 out of 166, and then 5 out of 166. And I know we've been pretty heavy on using the calculator. What I don't recall is if you can use the calculator with this information. Meaning I think you've got to do the by hand summation of observed minus the expected squared over the expected. Do you remember that from?
Yeah.
Okay, so what I mean by that is, do you have this 138 out of 166 value?
Yeah, I got 0.8313.
Okay, so that would be 0.8313 minus 0.7 squared over 0.7 plus, now we're going to do the one for 23 over 166.
Okay. Oh yeah, see here. 23.
So that's 0.1386 minus 0.2 squared over 0.2. Let me shift all this to the it's not going to do that. Okay, never mind. Plus, let's get the last one here.
0.0301.
Minus 0.1 squared over 0.1. So you have to do this calculation, get all these in there. So this might have been a good one to do in like a list, like this in list one. I'm sorry, the observed in list one as a proportion, expected in list two as a proportion, and then in L3 to do the L1 minus L2 squared over L2. That might have been a faster way to do it, but you got to come up with this this value here.
Right, right.
Is that clear?
Yes, that is.
Okay.
That is. I get that.
Now, that's only part of it. So the next part is we have to that's our test statistics. That's our chi-squared value. And I don't know, can you quickly get that for us, or is that too much effort?
Let me see. I mean, it might take a second for me to plug it all in, but I can sure try.
Okay, I'll do it as well. Since we probably really need this. Okay, I'm getting something that's not very large, which is not surprising given that I wonder, sorry, I'm trying to go back and forth here. I wonder if we were supposed to do this slightly differently. Now that I'm thinking, now that I see the way your instructor did this. So the other way to have done this, I'm sorry for being unclear.
Oh no, you're all good. Don't worry. It's both a learning process.
Is to use those percentages times the 166.2 times the 166, and that will give you the counts. And I actually do think that is what they wanted here.
What they wanted. Okay.
So what I said, maybe procedurally was correct. This is 116.2. 0.2 times 166 is going to give us 33.2. And then the last one is 16.6. So this one, it's 138 minus 116.2 squared over 116.2 plus 23 minus 33.2 squared over 33.2 plus 5 minus 16.6 squared over 16.6. Okay, and this looks like it's going to give us something a little bigger. Whenever we get this chi-squared value, we also need the degrees of freedom. The degrees of freedom in this problem is the number of rows minus 1. So in this case, it's 2 degrees of freedom. The total does not count. And then we want to look that up to find the p-value. So we can either use chi-squared, CDF, or a table, but we do need that numerical value here if we're going to proceed here. 138. Yeah, I'm already seeing a substantial difference. Okay. Five minus 16.6 squared. All right, so I get 15.33.
Yeah, that sounds about right.
And then I'm pretty sure, just based on the degrees of freedom, this area in the tail is going to be pretty small. Your p-value is probably going to be less than 0.05. Okay, so you would reject the null hypothesis. You would conclude that they're not random.
Right.
Okay. All right, so number 2 and 3 should be a little bit better. They're going to be more like the ones we've been doing. This is the one you should try entering into your calculator to get the, now that you've done the reset.
Right.
What we didn't do in the last one, I guess I should make a comment on that, is we did not do the whole, like, what are the conditions that satisfy this, but it would have been satisfied. This same thing, like, you need to look that the expected counts are bigger than
5.
Okay?
Yeah, and the 10%, the random, that whole spiel.
Yeah. So if you don't mind, will you try putting this into the matrix and doing your chi-squared thing and seeing if it works the way you expect it to?
Let's see. Oh, oops. Your matrix. And got it. So we got a 3, 2. 3, no, 2 over there. Oops. One. There we go. Okay. Yeah, now I got it.
I'm hearing success here. What'd you get for a chi-squared value on this one?
I got 0.6286.
Okay, and p-value is probably fairly large then.
Yeah, 0.73.
Okay, so this time your p-value is greater than alpha, so you fail to reject.
Right.
If it's less than alpha, you reject. The other one you fail to reject here. So I didn't even read it, but that's the scenario here with these two-way table type problems.
Okay.
You may want to write the null and alternative hypothesis, I suppose.
Yeah, the conditions and all that, but I can just run those up real quick.
All right.
I believe it does give the expected count now when I go, to B. And I
Yeah,
edit.
see if that's there for matrix B.
It does. It does give the expected counts.
Great. So I'd like to move to question 4. We'll come back to 3 if we have time, just to make sure we get everything, full coverage
Okay.
today on this.
Yeah, no, that's fine by me.
All right, so the way to read this table, this output that your teacher has here, is the coefficient here in your regression equation. It's beta 0 plus beta 1 x y. Or I'm sorry, those are lowercase. I guess I don't know if that matters. Are you guys using B0 or A and B?
We usually use beta sometimes, the lower or uppercase beta, but it doesn't matter.
So for the estimate, they're lowercase. For the null hypothesis, it would be beta. But for the actual least square equation, it's from the model. So the constant is B0, rho 1 is B1.
Okay.
You just have to grab those values from it.
Okay.
Minus 1.1171x. I think it's sometimes good to actually indicate what x represents. So like going back to the problem and figuring out like what is the input variable? Like what is it that they're measuring here? And the input or the independent variable is, I guess it's the distance or the seat location. I don't know. Let me.
Yeah. Does the C location matter? Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause high achievement, or do better students simply choose to sit in the front? An investigation was conducted where students were randomly assigned seat locations in a classroom and their scores on a test were recorded.
So X refers to some sort of like seat position or distance.
Right, like the row, like which row of
Okay.
seat closest
Yeah.
to the front of the classroom.
Yeah, so sometimes I even say that. I say like y is and I put in brackets the score, and x is the row, just to sort of indicate that I know that it's what it is.
Right, right, yeah. No,
that's a little extra. You don't have to do that. Part B here is to use your regression equation. Okay, so you have to, let me snip that in. You have to say, okay, got a student sitting in row 4. That's x of 4. 85.706 plus negative 1.1171 times 4. And you would calculate that value there. You generally want to give units. So in this case, at least say the score of.
I'm sorry, what'd you say?
You want to give the is as a units. Yeah, whenever you get this number, but you want to say like it's the score of.
Oh, the score of instead of,
or like let's just say it was that the output was dollars. You want to give it in terms of its variable output, unit output of the variable.
Right. Okay. I got 81.24.
Or sometimes they'll even say like interpret, and you would say a student sitting in row 4 should expect to receive a grade of 81.24 or a score of 81.24. All right, so
let's see. Interpret the score of y-intercept if possible and standard deviation of the residual. Isn't that the S right at the bottom? S equals 10.0673.
That is the standard error of the
standard error. That's right.
Of the equation. Trying to interpret the slope. So let's do the first one. Interpret the slope. Because it's negative, you know that there's a decrease. So you would say for every, and this is kind of the standard language, for every 1, and then you got to insert the x variable, row, back or away from the front. And then you would say and then this is now the y variable, the score. And then whether it's positive or negative, now we could say decreases by 1.1171.
Okay.
Now we'll look at the y-intercept. the y-intercept. So basically you have to decide, is row 0 meaningful? So let me give you a better example. Is a shoe size of 0 possible?
No.
No. So that would not be meaningful. Now, row 0 could be, like I've been to places where there is a row 0. All right.
Right.
I'm not, that's where it's a little bit, this one's a little bit vague. You have to decide if 0 is even possible. So depending on how you argue it, I could could say, well, 0 means they're sitting in the front of the room. 1 is the first row from the front. I'm not sure. Do you get like a solution guide to go with this?
Yeah, I can pull up the solution.
Why don't you see what
she had in mind?
Yeah.
So for that we go there, all the way here. Okay, so it says for slope, it equals negative 1.1171 over 1. So for score and row, it says as students sit further away as they increase row number, the predicted score goes down by 1.1171. Typically, predictions of score will be off from the actual values by 10.063 on average.
Okay, so that sounds like the standard deviation of the residual, but she didn't really answer whether row 0 is meaningful.
Yeah, no, it doesn't seem that. I mean, she just put the standard error right under it.
Yes, so I don't really like that language, but that's, go with what your teacher wants. So if they ask about the standard deviation of the residual, you're looking for this S value right there.
Standard deviation of the residual. Okay. Interesting.
All right, the part D here, the standard error of the slope, we do get that from the table here. Let me grab the table again. So the standard error of the slope is a value in the table. The slope is the second row. There's the standard error of the slope right there.
Standard error of the slope. So like another thing is like making sure you know like which number of those is like asked for, not asked for, but like what each number is basically. And like
exactly. So there's a bit more here, and I don't know if you've seen this in class, but like the coefficient is what we talked about. That's fine. The standard error is what we just talked about. The t value is the division of these two numbers. 85.706 divided by 4 gets you to the 20. The p value comes from the t value here. Like that's the using the distribution here of like, okay, there's 20, how much area is to the right? 0, things like that.
Okay, I see. Right. That does make sense.
It's two-tailed typically, so that's why in the second one here, because it's minus 1.18, it's about there, and there is some error, there's some there, but I believe it's two-tailed. I have to double check that to be sure.
Okay.
The S we just talked about, the R square, you're not going to use the adjusted value. You're going to use this one. This is the percent variation in the output described by the input. So the better way of saying this, especially in this problem, it describes how well does the input variable, which is rho, actually contribute to the score. And it's only 4.7% of the way to predict the score, which is not very good.
Yeah.
It's not very good at all. That means there's other variables in play, like maybe how well you pay attention in class or do your homework, stuff like that. But you're right. You do have to know stuff from this table. There are other things they could ask you here. Okay, calculate the 95% confidence interval for the true slope. This is actually done in software most of the time, but the confidence interval, as you know, is X bar plus or minus. In this case, it's going to be T. I'm sorry. Yeah.
Yeah.
T alpha over 2 S over square root of N. The X bar is the slope. I guess I could say that. The T is not the T that's given there. That's the, this isn't right. This is the C. No, it is based on C. So you need to know the degrees of freedom, which I'm not sure you know from this, unless you're supposed to assume that it's a normally distributed, which is not true. It's a T distribution typically. You might want to ask about this one, especially because it says show your work, or pull up the answer because we're running.
Yeah, no, let me see.
Running out of time. The answer to part F is based on how wide that interval is.
Oh, okay. I see what you did.
It's based on how wide and if it includes 0 or not. Because if it includes 0, you don't know whether it's positive or negative slope.
Okay.
Which means it may not increase or decrease your score. And then final thought here. How would you carry out an appropriate test to answer F? I don't know, whatever she says, go with that.
C locations. Yeah, no, I got all the answers on this side. So it just says no, since 0 is in the interval, 0 means there is no linear relationship, so it doesn't guarantee that row affects score.
Yes, exactly. You don't know whether it's increasing or decreasing, so sit wherever you want, kind of thing.
Right. Yeah, exactly.
All right. We do